8.3 Graph General Rational Functions. The comic of the day is something I actually want to teach you today. It says, psychology test, is the interval half open or half closed? Something we have not talked a lot about this year is interval notation. And it's a really great shortcut when you want to express things like the domain and the range. An x value, for instance, that can be between two numbers can be expressed with interval notation like this. If I say 4 is less than x, which is less than 6, that means that x lies between 4 and 6. Between 4 and 6. Since it's not included, I put open parentheses. So that would say half open would be those parentheses like that. Now if I instead wanted to do 4 is less than or equal to x, which is less than or equal to 6, so that includes both 4 and 6, then I would use the brackets instead of the parentheses. And that means that it's a closed interval, meaning it includes those numbers. I can also have an interval that is half open, half closed. Let's include the 6. Let's include the 6, but do not include the 4. So the 4 has the parentheses. Okay, so this would be the open circle here and a closed circle here because only the 6 is included. Again, to summarize, if you want to include the number, then you use the bracket. If you want to not include the number, then you use the parenthesis. We did touch on this before. Remember, we were doing something like x is greater than 8, and that meant we went from 8 to infinity. Infinity always has a parenthesis on it no matter what. So x is greater than 8 would be 8 on. X is greater than or equal to 8 would be 8 is included on. The infinity, it can't be included. You can't touch infinity. Can't be included. Same thing goes with negative infinity. Today we're going to be graphing rational functions of the form f of x equals p of x over q of x, where we have no common factors. To find what the x-intercepts are, we want to know when the fraction equals 0. The only time a fraction equals 0 is when the top equals 0, since the bottom can equal 0. So to find the x-intercept, look for where the numerator equals 0. To find the vertical asymptotes, just think the vertical asymptote is like what x cannot be. So if we're talking fractions here, just look for where q of x is equal to 0. Okay, so you shouldn't be memorizing anything. The x-intercepts just mean, where does this thing equal 0? If a fraction equals 0, it means the top must be equal to 0. Vertical asymptotes are just like, what x values do we never touch? Well, we never touch the x values when the denominator equals 0. If we set the denominator equal to 0, we're going to get x equals something, and those values can't hold true. So that's a vertical asymptote. Now to find the horizontal asymptote, that's a little bit harder. The horizontal asymptote is getting at the end behavior. Meaning, what happens as x gets huge or tiny? So think about, if the degree of the numerator is less than the degree of the denominator, that means the denominator is the larger thing. I'm going to just underline what's larger. Since the denominator is larger, we have small over big. Take a small number like 1, divided by a big number like 1,000,000. You get practically 0. You can try it on your calculator. So that would give us y equals 0 is our horizontal asymptote. If the degree of the numerator equals the degree of the denominator, well, now neither of them are larger. They're the same. So we just take the ratio of the coefficients, and that is going to be our horizontal asymptote. This probably doesn't make any sense, so let me just show you what I mean over here. If I have y equals 2x squared plus 7x over, let's say 5x squared plus 8, since the degree in the numerator is equal to the degree in the denominator, the horizontal asymptote is just going to be the ratio of the leading coefficients. So in this case, 2 over 5. Okay, so that is what I mean. Finally, if the degree of the numerator is greater than the degree of the denominator, so now the numerator is bigger, so now we have big over small. Take a million divided by a really small number. It's going to be so humongous, like infinity, and we can't touch infinity. So this means that we have none, no horizontal asymptote. Let me do some examples, and this will make a lot more sense. So in order to graph this, let's first look at our x-intercept, our vertical asymptote, and our horizontal asymptote. Our x-intercept is going to be where does y equal 0. The definition of x-intercept never changes, ever, ever. That means when does 0 equal -2? Well, that just doesn't happen, ever. So there is no x-intercept. What is a vertical asymptote? That's what can x not be. So look at when the denominator equals 0. When does x squared plus 2 equal 0? In other words, when does x squared equal -2? Since we're dealing in the real number system now, we have no vertical asymptote because something squared cannot be a negative number if it's real. Now let's go for the horizontal asymptote. You see that the degree in the denominator is larger than the degree in the numerator. In other words, for a horizontal asymptote, we have a small number over a huge number. Small over something huge, take a small number, divide it into a huge number of parts, that's practically going to be 0. In other words, our horizontal asymptote is y equals 0. So we can draw that in. And then maybe let's just pick 3 other points. Let's definitely do when x is 0, and then let's just do -3 and 3. So if I put in -3, we get -2 over -3, the quantity squared plus 2, which is -2 over 9 plus 2 is 11, -2 11ths. If I put in 0, I get -2 over 0 squared plus 2, which is just -1. And if I put in 3, well, 3 squared is the same thing as -3 squared, so I get -2 11ths again. And so let's just plot those 3 points. Now, I know that we're going to practice symmetry here. Since I'm squaring it, you'll see that the -3 popped out the same thing as the 3. And I'm getting so close to the asymptote, but remember, I can't touch it. And so my graph is going to look something. I didn't do a great job drawing that picture at all. If you blew it up, it would look more like that. But I was having a hard time because I probably should have changed the scale of this. Anyway, what's more important is let's go for the domain and range right now. The domain is clearly all real numbers. It's not restricted what x values can go into this. But what is restricted is our range. Our range, you can see, the biggest possible thing is 0, but the 0 is not included. The smallest thing that we ever get is the -1, and it does actually touch -1, so the -1 is included. So if you want to write it like that, I think that's a shortcut. If you want to write it like -1 is less than or equal to y, which is less than 0, you can write it like that also. This is what we call interval notation. Let's do the same thing in this example. Let's start with the x-intercept, then let's do the vertical asymptote, and then let's look for the horizontal asymptote. The x-intercept is just going to be, where does this guy equal 0? So when does -x squared equal 0? Well, that's just when x squared equals 0. In other words, where x equals, you could say plus or minus 0, which is just 0. So the x-intercept is going to be 0, meaning it goes through the point 0, 0. What is the vertical asymptote? The vertical asymptote is what x cannot be. So when does the denominator, in other words, x squared minus 4 equals 0? Well, that's when x squared equals 4, x equals plus or minus 2. So x equals 2 and x equals negative 2 are our vertical asymptotes. Let's draw them in at negative 2 and at 2. Finally, how do I find my horizontal asymptotes? You'll notice that the degree of the numerator and the denominator is the same. So what is the ratio of the coefficients, just negative 1 on the top over 1 on the bottom? That's just negative 1. So y equals negative 1 is going to be my horizontal asymptote. Now let's plot the point we know, 0, 0. And to make our best graph, it would be great to pick 3 points in this region, 3 points in this region, and 3 points in this region. Since I know the graph is going to be here, I can assume that we're going to have a graph looking like up here. We're going to have a piece of the graph going like this. And we're going to have a piece of the graph going over here. But that's just my first little sketch that I think it's going to look like. And I'm going to justify that with some XY points that I'm going to pick. But how I just figured out this real quick sketch, if I were pressed for time, is just by looking at the asymptotes and kind of filling in the rest. Typically with these types of rational functions, you'll see them like switching sides. You see how I did that here? Since I knew that this point was a point, I knew that my graph had to look in between the asymptotes over here, so it really could only look like this. And then I just thought what made sense over here, it would be getting close to this asymptote and close to this asymptote, and I knew it had to be on this side because, again, it usually flip-flops sides. So you'll start seeing that more as you see more and more graphs and get used to it like I am. Let's pick some XY points. Why don't we just pick negative 5, maybe negative 3. Then in the next interval, I guess we should have negative 1 and 1. And then in the next interval, well, why don't we just do 3 and 5? So when I put in a negative 5, I do the opposite of negative 5 squared. Remember your order of operations. This is the opposite of negative 5 squared. And then on the bottom, we have the whole negative 5 squared minus 4. So we have the opposite of 25 over 25 minus 4, which is negative 25 over 21. So that's going to be a little bit more than negative 1. Let's put in negative 3. Again, the opposite of negative 3 squared over negative 3 squared minus 4. That is negative 9 over 9 minus 4. Negative 9 fifths. That's almost negative 2, but not quite. Now let's put in negative 1. The opposite of negative 1 squared over negative 1 squared minus 4. Well, that is the opposite of 1 over 1 minus 4, which is negative 1 over negative 3, or 1/3. Now, when we put in the 1, we were doing the opposite of, and then 1 squared is going to give us the same answer as that negative 1. So we are going to get 1/3 here, and the only reason we can practice at symmetry is because each of the x's are being squared. If anything had been cubed, or if we just had x alone, we wouldn't have had that beautiful symmetry. Now for the same reasons, it goes with the negative 3 and the negative 5. You can test it if you don't totally understand what I mean by that. Now you'll see on this side I did a pretty good job. I didn't practice very good symmetry here. At negative 3, I went to almost negative 2, but not quite. Negative 5, I just went down a little bit. So let me clean up my graph. Again, I know that it's got to get real close to these asymptotes, but not quite touch them. Do my best at practicing symmetry over here. Let me just do my domain and range while I'm at it. My domain is going to be all real numbers except x equals -2 and x equals 2, right? Because it's all numbers except here and here. An easier way to do this might be with our interval notation. So it goes from -infinity, it goes to -2. It doesn't include -2. Then it goes until 2, so we go from -2 to 2. And then we go from 2 on, right? We went from -infinity to -2. Then we went between there, -2 and 2, and then we went from 2 on. What is our range? Our range would just be all the way down here to -1. So all the way down there till -1. It doesn't touch -1. And then look, it doesn't pick back up till 0. So we don't pick back up until 0. And then we go on and on and on. So again, the y values, what does it touch? It touches all of them from -infinity to -1, just doesn't include -1. And then we don't pick back up on the y values until 0 on. So that's the range. Finally, example 3, let's do the same thing. X-intercept, vertical asymptote, and horizontal asymptote. X-intercept, where does y equal 0? So just make that numerator equal to 0. Let's factor that guy. X and x, a 1 and a 1, negative and a negative. So x equal 1 is going to be my x-intercept. So that's the point 1, 0 that it's going to go through. The vertical asymptote, what can x not be? So that's when the denominator equals 0. X equals -2 is our vertical asymptote. So let's put that in. 1, 2. And that's our x-intercept. Our horizontal asymptote, well, the numerator is bigger than the denominator. So we have huge over tiny is going to be something humongous. In other words, there is none. Because it's so big, it goes off to infinity, and we can't touch infinity, so there is none. So now let's just put in some points over here, and put in some points over here. Let's do -5, -3, and then let's put in 0 and 3. We cannot assume symmetry here, of course, because we are not squaring everything at all. So let's do the -5 first. So we have -5, the quantity squared, minus 2 times -5 plus 1 over -5 plus 2. In other words, 25 plus 10 is 35, 36 over -3, which is -12. So I'm going to scale this. So this is -2. But I'm going to keep this scale, so that's just -1. So -1, 2, 3, 4, 5, 2, 4, 6, 8, 10, 12. Let's put in -3. So we have -3, the quantity squared, minus 2 times -3 plus 1 over -3 plus 2. So we have 9 plus 6 is 15, 16 over -1, -16. All right, 0 should be nice and easy because we just get 0 minus 0 plus 1 over 2. That's just 1/2. And then when we put in 3, we get 3 squared minus 2 times 3 plus 1 over 3 plus 2. Bottom is 5. The top is 9. 9 plus 1 is 10. 10 minus 6, 4. So that's almost 1, not quite. Remember, I went up by 2's. And so in this one, it's not going to practice any symmetry, and you're really not going to know exactly what this looks like unless you look at your calculator. But it looks something like this. You'll learn more about how to graph these things next year. This year is really just a quick preview. but it's going to look something like that. We're not going to learn about slant asymptotes or any of that this year. Something to look forward to next year. But just remember, this one just does not practice any symmetry, so we know it's going to look wacky. I'm not going to ask you to find the range of this one without your calculator, because you would need to find the mins and the maxes in order to really do this, since you can't do that by hand right now. And you could find the domain, because the domain is just all real numbers except for -2. And that's it for this lesson.
Bye.